Hello, a very good evening to all of you. Today, we are joining with another session of Qiskit 2025 Fall Fest. Today, we are going to discuss Introduction to Qiskit. This webinar will introduce the basics of Qiskit, exploring its core concepts and the fundamental theories that supports its use in quantum computing. Before starting, let me remind you of our timeline. So we are on 29th of October. Today, we are going to do the session on Introduction to Qiskit, and there will be an in-person workshop on 7th November. And to finalize the information about the speaker, we'll this information as soon as possible. Information is finalized, we'll update you soon regarding the event. And again, we have the Q Extreme Hackathon starting on 12th November as well. It would be a 5-day hackathon. So without further ado, let's dive into today's session. Now, I'd like to invite our today's speaker. Over to you, Lisitha.
Good evening, guys. I'm Lisitha Dissanayaka from University of Colombo. I'm 30-year undergraduate. I'm 30-year undergraduate, and I am IBM Qiskit Advocate. This is the second session of Qiskit Fall Fest 2025, and you guys participate for introduction to quantum computing in quantum computing in our first session, and this is our second session. Today we are talking about Qiskit, introduction to Qiskit for quantum computing. If I talk about me, I have a 2 to 3 year experience with Qiskit for quantum computing, and I have do some projects and hackathons by using Qiskit. Qiskit. Okay, let's move to today's agenda. This is our agenda. We are first of all we are introducing Qiskit, and we are talking about what is it and why it's important, and then we are talking about Qiskit quantum circuit, understanding the building blocks of quantum computation and quantum gates, how qubits are manipulated using quantum gates. And we are also talking about Qiskit workflow, the step-by-step process of building and running Qiskit. There are 4 Qiskit workflow, 4 steps in Qiskit workflow: build, transpile, verify, and run. I will explain one by one what are those things and what we are doing in each of the steps. And next one is we are talking about what are the prerequisites needed for the program quantum computers with Qiskit, and we are installing Qiskit for your system, and we are creating IBM account to access IBM real quantum computers. Without IBM account, we can't do that. Because of that, we creating IBM account today, and we are learning about how to manipulate qubits, and we learn about what is relative phase, what is state, what is probability of quantum states, and we also learn about measurement in quantum circuit, measurement in quantum circuits, and we are running quantum circuit in quantum simulator, and then we run our quantum circuits in real quantum IBM quantum computers. And we deep dive into quantum computing by learning multi-qubit gates. And we are in this section, we are learning about what is entanglement and how to deal with how to qubits are interact with each other. Okay, let's move on to what is Qiskit. Qiskit is an open source software development kit for working with quantum computers. It allows you to create, simulate, and run quantum circuits and manipulate quantum operation at low level. Qiskit ecosystem provide additional tools like tutorials, libraries to extend its capabilities and helping both beginners and advanced users for explore quantum computing. For more information, you can check these links provided by IBM for IBM documentation and Qiskit ecosystem website. Okay. Okay. Mm, uh, mm, okay. Today we are using Qiskit 2.0. I will introduce Qiskit. What is Qiskit 2.0? Qiskit was initially released on 2017 with the major milestones are released in release 1.0 released in 2004. 2024 and Qiskit 2.0 released in 2025. Qiskit 2.0 is significant because it introduced a C API in latest version. I mean, Qiskit 2.0 is the latest version. Qiskit 2.0 is significant because it is introduced C API, allowing a developer to use Qiskit without Python and providing a way to multi-language support, and it can be used either as a standalone C library or embedded with Python. I think Qiskit IBM introduced Qiskit C API for Qiskit because of the C is more faster than Python. And if we move on to other highlights of the Qiskit 2.0, it's a trust-powered performance improvement, which make Qiskit construction and transpilation much faster. Support for abstract timing in dynamic circuit and new box functionalities for atomic blocks in transpile. Although the C API is minimal today because it is alternatively growing and documented in C API reference. Okay. Qiskit SDK. Let's talk about what are the potentials in Qiskit SDK. There are many. The only quantum programming language. Qiskit is not the only programming languages for programming quantum computers. There are many programming languages like Penny Q#, but the Qiskit SDK is the widely used quantum computing SDK. You can write quantum circuits once and write it more than 10 different quantum computers. According to the Unitary Foundation survey, Qiskit is the most popular quantum SDK, and it's worked with the many hardware providers, including IBM Quantum, AQT, AQM, Azure Quantum, IonQ, Quantum Backers, Alice and Brigitte are some of the quantum hardware providers. All these hardware are compatible with Qiskit. About 74% of Qiskit contributors are from outside of the IBM, showing it is used and supported by large community. There are also over 5,000 projects that depend on Qiskit and providing a wide impact for world. These are the benchmark of Qiskit SDK. Now, in speed test, it can complete tasks around 5 minutes, while some competitors take about 24 hours. In quality tests, Qiskit maintain constant high quality result for circuits, even with many gates. It is also a highly extensible with over 4,000 plus dependent project. 4,000 dependent project compared to 1,000 for about 1,000 for Penny and 100 for CERN platforms. Qiskit leads with 24%, followed by Qiskit AER at 49%, and Penny with Penny at 47% These results are reported by bench press test on roughly 1,000 circuits, showing the Qiskit performance and reliability across the many real-world scenarios. Okay, let's move on to today's today's session. This is the core concept we are learning today. So, what is quantum circuit? What is quantum circuit? The name can be a bit misleading for you because when we think of circuit, we usually imagine something like this: a traditional, something like this, like a traditional circuit with wires. See, you can see here. Wires, resistors, capacitors, transistors, and diodes, and then current flow through a physical connection, and components manipulate voltage and current. But in when we are talking about quantum circuit, it's not about that. In here, we are not really connecting wires and resistors in traditional sense. Instead of that, we connect states. What we are called as, we name it as quantum states. Quantum circuit is actually a computational model, and it is a sequence of quantum gates applied to Qiskit over time. In here, you can see that the horizontal line. Each horizontal line here is labeled as Q0, Q1, Q2, Q3 represent a qubit to represent a qubit. It's not a physical wire. Don't confuse with these wires. These are not physical wires. These are representation of time. And you can see here the boxes like the structure like H gate and Z gates and measurement symbol represent quantum operation that transform the quantum states. In here, times flow left to right, and we start with qubits in initial state and apply to manipulate them through a superposition, entanglement, quantum computational. And finally measure them to get classical output. And this is the exact what Qiskit allows us to do: build, simulate, and run this quantum circuit in quantum circuit. Okay, let's move on to what are the components in quantum circuits. Quantum circuit is the basic model used to describe and run computations on quantum computers. It is essentially the quantum equivalent of classical algorithm. A quantum circuit consists of three components. Let's talk about qubits. Qubits, these are the fundamental units of quantum information, similar to how bits are the basic units in the classical computing. But unlike classical bits, that they are in classical bits, the state is deterministic. We have only 0 or 1. But in qubits, there can the qubits can exist in superposition state, both states simultaneously. And then second, quantum gates. These are the operations that change the qubits state. Think of them as analogs to quantum gates in classical circuits, like AND, OR, NOR, NOT gate. But quantum gates can create superposition entanglement, giving us a quantum advantage. Finally, measurements. These are the steps that read out quantum values after computation. When we measure a qubit, it has a superposition color to either 0 or 1, give us a classical output. Okay, now here with the Qiskit, and we can see a Qiskit Python object where you can add gates, visualize the circuit, and execute in simulator or real quantum device. it is okay. Let's move deep dive into what are the quantum gates. Their quantum gates are in quantum gates. Actually, there are two types of quantum gates. One is single qubit gate, and one is multiple qubit gates. First of all, I will introduce what is gate. Uh, uh, in this table show that the most commonly used quantum gates in quantum computing. For each gate, we can see three representators: the operator, gates, and matrix. This is the name operator name, and this is the gate we are denoting in the quantum circuit, and this is the matrix transformation we done for qubit. If I talk about first of all, I will talk about single qubit gates. These are the single qubit gates. Pauli gates X, Y, and Z. These are the quantum gates of classical NOT gates. And they are the X gate flip qubits from 0 to 1 or vice versa. And the Y and Z gate also flip the state, but at different phase changes. We will learn about what are phase changes later in this session. And this is Hadamard gate. Hadamard gate is considered as the most important gate in the quantum computing because it's gate superposition, taking the qubit from the definite state 0 and putting it into equal superposition of 0 and 1. This means both states are in superposition, in 50-50 superposition. And if we move on to the multi-qubit gates, C0 gates, and we also call control NOT gate, is a 2-qubit gate. If the control qubit is 1, if the here this is the control qubit and this is the target qubit. If control qubit is 1, then target qubit is flip the state. If the control qubit is 0, the target qubit do not change the state of state, and it is stay as it is. This is a matrix for the control NOT gate, and there are also multi-qubit gates called swap. Swap is swapping the states of states between two qubits. These are the basic gates that we need today, and there are many, and also there are many qubit gates if you will learn quantum computing further. Quantum circuit. Quantum circuit. First, to design a quantum circuit with Qiskit, we import what we need from the Qiskit circuit, Qiskit register, and classical registers. Next, we define our register. In here, you can see we define our register. And then we define our classical register. These classical registers are needed to store the measurements we are taken from these qubits. This is a barrier. This barrier is not and this barrier is not effect for the quantum gate. This is just for the clearance of the quantum gates and to make more understand more understand the quantum gates. This is called a C0 gate. In previous slide we saw that this is C0 gate, and we apply that C0 gate in this circuit. And this is Hadamard gate. I explained the Hadamard gate in here, which is an important gate for make superposition. And this is how the structure of Qiskit code is look like, and we can draw our circuit by using Qiskit Qiskit SDK. Okay. Let's move on to the Qiskit workflow. Qiskit introduced 4 steps for compilation of the Qiskit. Let's now we are in later we in previous slide we are seeing how to create quantum circuit, and let's understand the complete Qiskit workflow. Qiskit organize quantum computing into 4 clear stages, taking you from initial design all the way to execute on running a real quantum computer hardware. Build. This is where everything start. In the build state, you build phase, you design and develop quantum circuit. And in this way, this is where you define your bits, apply gauge, add measurement, and essential writing your quantum algorithm in code, just like we saw the previous slide. This is your creative workplace where you translate quantum ideas into actual circuits. Transpile. In transpile, once you have build your circuit, you need to transpile. The meaning of the transpile is optimize your circuit to efficiently run on specific hardware. Why? Because the real hardware has constraint. Not all qubits are connected to each other. Different devices support different negative sets, and there are error rates to consider. The transpiler adapt to your ideal circuit to work within these real world limitations and optimize your target devices in topology and get set. And then let's move on to the verify stage. In before verify stage need when we before run on expensive quantum hardware, you want to validate and evaluate your quantum circuit. This is where you can simulate your circuit and check if it doing what you expect, analyze it properly, and estimate how it might perform. Think of this as your testing and debugging phase. This is like a debugging phase in normal software development approach. In final stage, finally we are in the run stage. In this stage, you are execute your program on hardware via quantum runtime. This is where your circuit run on actual processors, where that's IBM's quantum computers or simulators like AER simulators. Qiskit runtime provide an optimized execution environment that handles the submission and manage the queue and return your result. These 4 stages build, transpile, verify, and run. Build, transpile, verify, and run form a complete pipeline from quantum algorithm designed to real-world execution. Qiskit provides a comprehensive documentation for each stage, and you can find all the in detail of these each phases in these links. I will provide slides for you for follow these links. Okay, let's talk about each of the stage one by one. Build stage. In build stage, you can create quantum program that represent the problem you are solving. In this stage, we are designing your quantum circuit, and if you are developing an algorithm and all the algorithm, all the circuits that regarding this algorithm is you are writing in here. And initialize registers at qubit on the circuit and perform operation on those qubits are done in this build phase. The output of quantum circuit is encapsulated by primitives. Primitives are quantum computation building blocks that define what the exact information of quantum circuit. Think of them as standardized interface for quantum computer programs. There are 2 main types primitive in Qiskit. They serve different supports. The sampler primitive, and estimator primitive. If we talk about sampler primitive, the sampler gives us probabilistic distribution over a possible measurement outcome. In other words, this tells us if we run this circuit many times and measure it, what the probability of getting each possible result. In this graph, you can see that the visualize as a probabilistic distribution, showing you can likely each measurement outcome is. Likely each measurement outcome is. For sampler, your circuit should include measurement. See, these are the measurement gates. In sampler, you should include measurements. The sampler, you are essential to run your circuit multiple times, collect all measurements result, and build the statistical distribution from them. This is useful when you want to sample from quantum state, for example, in quantum sampling algorithm, or when you are interested to full probability landscape of your quantum computations. The estimator primitive. The estimator primitive is different. It gives an expectation value of observable. For example, expected cost function value in optimization problems, and instead of a fully probabilistic distribution, you get a single value with error bars. The average outcome to expect if you measure and particular quantum observable. For the estimator primitive, your circuit should not include the measurement. The estimator handles the measurement process internally based on observable you specify. You can see the circuit has no measurement in here. You can see there is no measurement case in here, like in sampler primitives. This is particularly useful for variation algorithms, and where you are try to minimize or maximize expectation value. In summary, we use sampler when you want to sample measurement outcomes and see probability distribution, and use estimator when you want to compute expectation value of observable. Both are fundamental primitives encapsulating how we extract meaningfully full information from quantum circuits. Okay. Qiskit includes standard gates and circuits that you are ready to use. There are these standard gauge includes things like Hadamard gates, what we talked in the previous slides. In standard gates includes things like Hadamard gate, Pauli rotations, and C-node gates, and even quantum Fourier transformation gates. And what are these are the building blocks for most quantum algorithms. And Qiskit also provides the benchmarking circuit, which help us to test the performance of your circuits. As example, quantum volume circuit, randomized benchmark circuits. For more advanced application, Qiskit includes variational ANSACs, which parameterize circuits and used for computational chemistry and combinatorial optimizations. And some are hardware efficient, and meaning that they are designed to work well in real quantum devices. But for today's session, we are only using standard gates. For benchmark circuits, we only use this measurement gates. We're not talking about we are not take hands-on experience about the variation and analysis gates and common circuits. Okay, let's move to next phase. We have four states. For step in Qiskit compilation workflow, we talk about what is built, and then we should talk about this as a second phase transpile. When we run a quantum circuit, on a real hardware, it often needs to be transformed or rewrite to match the device capabilities, because all the hardwares are not compatible with all the all the quantum softwares. with the meaning of quantum software is quantum circuits. All the hardwares are not all hardware is always not compatible with the software are written by Qiskit. So we need transpile. Transpile is the transformation and or rewrite your circuit into efficient way to run in executing quantum device. Real quantum devices have constraint like these are the quantum constraint that are in real quantum devices. They can only execute a limited set of gates directly. Directly, they can execute only limited gates. So we must rewrite our quantum circuit, means our quantum software, to available on those hardwares. And only create pair of qubits can interact directly. Only a certain pair of qubits can interact directly. So the gates might be needed to rearrange. And every operation has a chance of error. So we should optimize the circuit and improve the reliability and performance of our circuit. The transpiler is can done automatically by the Qiskit SDK. They provide the infrastructure for the transpilation for the Qiskit circuit developed by Qiskit. This is transpile circuit. In Qiskit, when we in Qiskit, you can transpile a circuit automatically to prepare it for a specific quantum backend. First, you choose a device. In here, we choose a device and device that you want to run, and then you generate present pass manager with desired optimization level, and this is optimization level in here. And finally, you run a pass manager on your circuit and provide a transpile circuit that respect hardware constraint, uses only available gates and minimize error. The resulting transpile circuit can be visualized, and in this code piece, we can visualize this transpile circuit. This transpile circuit is done automatically by Qiskit. You don't need to write from scratch for this. You don't need to write from scratch transpile circuit. Since you don't need to transpile your circuit and submit them to Qiskit Advocate. But for best performance, you should design your transpilation pipeline your own. If you want to transpile your circuit locally, you should skip transpilation equal true. So the Qiskit SDK don't do the transpilation process. Okay. So we talk about build and then transpile, and we move on to the verify stage. In verify stage, you test your quantum program by running them on simulated devices and exploring their performance under realistic device noise model. This is your testing. This is your testing and validation environment. In typical software development process, you have testing phase. Similarly, this verify phase is used for the verify your design software. Now simulating a quantum circuit comes with important because the cost of the simulating quantum circuit shares exponentially with the number of qubits. What does it mean? As you add more qubits, the computational resources required to simulate the circuit grow exponentially. This is actually one of the reasons that the quantum computers are powerful and they can handle computation that classical computers struggle to simulate. If roughly speaking, that the circuit larger than 50 qubits can't be simulated on classical computers with reasonable resources and time. 50 qubit is roughly the boundary where quantum advantage begins and where quantum computers can do things classical computers practically cannot. So what you do if your circuit is larger? For larger state, for larger quantum circuits, you have a couple of strategies. First, test a small version of your circuit. You can validate your logic and approach on scaled down version with fewer qubits. And if the smaller version works correctly, you have a confident and the full circuit can be run in real hardware. The second one is modify circuit so that it become classically simulatable. For example, you could create what's called stabilized. For example, you create what's called a stabilized circuit. We will learn what is stabilized circuit in next slide. Restrict the class of quantum circuit that can be efficiently simulated classically, even with many qubits. This won't give you the full quantum behavior, but it can help you to verify certain properties to design in your quantum circuit. In the verify phase is all about gaining confidence in your quantum program. Before you use valuable quantum hardware time, simulation help you to debug. Help you to debug, optimize, and understand your circuit in controlled environment. Okay, let's move on to simulation tools. Qiskit AER is a simulator. Qiskit AER provides high-performance quantum circuit simulators that you can use during the verify phase. Qiskit AER is incredibly versatile, and it's allows you to test and debug quantum circuit, analyze noise effect. Noise effect means simulate reality. The AER can simulate the realistic noise model to see how your circuit would behave on actual noisy quantum hardware. Benchmark algorithm compare different approaches and optimize performance. Compare simulated result with IBM real quantum computer hardware, and you can validate your simulation against actual quantum computers. So instead of sending your circuit to actual computers, you can use AER to simulate it locally or on cloud CPU or GPUs. It gives fast iteration cycles during development. You can certainly test and debug and refine your circuit quickly without sending it to real quantum hardware. These are the four types of quantum AER simulators: state vector simulators, QSMA simulators, which mean quantum assembly simulators, density metric simulators, and unitary simulators. These are the simulators provided by AER simulator. You don't need to know more detail about what these simulators are do. If you are learn more about quantum computing, you will learn this the usage of each of these simulators. Simulating quantum noise by Qiskit AER. In real quantum devices are not perfect. They are subject to errors. The amount of errors can vary depending on the devices, which qubits or connection are used, and even the time at which the computation is run make noise. In the near term, we use various error mitigation techniques to reduce the impact of noise and get more accurate result more accurate result in long term. We aim to implement quantum error correction, which will allow you to build fault-tolerant quantum computers that you can perform reliable computation despite quantum hardwares. This is how build the noise modeling quantum area. Today we in our hands-on session we do not implement these noise from scratch, but this is for your knowledge. One of the most powerful feature of the AR is the noise modeling. You can use Qiskit AR to build and simulate noise model, and that reflect the real quantum computer hardware imperfections. And it can initialize a noise model with parameters set from collaboration data of real vacuums. And this means you can take actual error rates and decoherence time from IBM quantum computers and simulate how your circuit would perform on a specific device without waiting in a queue. And you can also build in your own custom noise model from scratch. If you want to set the specific error scenarios, you can hypothetical and you can implement hypothetical errors. For example, the most quantum depolarization error is one of the quantum condition that error condition, most popular error noise model, and with probability P, the quantum stage get randomized, and you can apply this and other errors type of specific gates in your circuit to create realistic simulation. Noise modeling help you to understand how robust your quantum algorithm before it commit to real hardware. Let's move on. This is a transpilation optimization method. I do not explain much more about this stabilization circuit. I will provide this slides and you can learn more about what are stabilized circuit. This is stabilization is the method of verifying your circuit. Okay, we talk about three phases. Now, among four phases, we talk about three: build, transpile, and verify. Then we are move on to run. Run means you are in run phase. You are sending your quantum program to execute it on quantum system. Before you are learning about how to execute a quantum execute your quantum circuit in real quantum hardware, you should learn about the anatomy of quantum computing service and how your code become a real quantum computation. You write your quantum programs using programming like Qiskit, and the cloud services such as Qiskit Runtime, send your Qiskit Runtime send your job to quantum hardware. Then it managed to execute. The server in the laboratory receive the job and communicate with hardware to control electronics. These electronics generate pulse sequence in the physical instruction with manipulate qubits, and finally the quantum processor perform a computation and the measurement result, and then send back it through the same chain. The result is sent back to your PC. This layered structure ensured you can program quantum computers remotely without worrying about the hardware details. These are how this is about how to run a circuit on quantum hardware using Qiskit Runtime. We will learn more about this in our notebook section. This is an about the Qiskit runtime, how jobs are queued for real quantum hardware. Um, mm, Quantum hardware and Qiskit and this image is illustrate the Qiskit ecosystem and how bridge software and hardware in classical and quantum classical computing. Qiskit acts as a software layer that manages workload for both quantum and classical computers, and it operates within quantum classical ecosystem that includes quantum computer and high performance classical computer. The quantum computer components consist of Qiskit runtime, a quantum processing unit that quantum chips and high performance classical compute performance classical compute component includes GPU, CPUs, and APUs. These are the inside. This is the full Qiskit stack and how quantum classical workloads are distributed. And this is abstraction service development tool and heterogeneous orchestration layer and compute. We talked about this layer in the previous slide, and this is how the Qiskit stack work. And let's move on to our quantum journey with Qiskit. Before moving on to the Qiskit, you should have prerequisites to start learning Qiskit. First of all, you have a very basic foundation of quantum mechanics, not in a deep mathematical way, but in conceptual level. Like you should have a small knowledge about what is conceptual. Wide knowledge about what is superposition, what is entanglement, what is quantum decoherence, what is quantum noise. And you should also have a basic idea about complex numbers, and you have to familiar with the Jupyter notebooks. For our today's session, we are using Google Colab. And also there is a specialized Jupyter notebook called QBrate that is specialized for quantum processing, quantum program writing, and in default they have most of the quantum SDKs, and you have to have basic Python programming knowledge, and you have a basic understanding about linear algebra, and you have to IBM account for run your quantum your designed quantum circuit in real quantum hardware. Okay, I will share my screen for creating how to create a quantum IBM account. I will share my screen. Wait. Okay, I think now you can see my on screen. Wait a minute. To create quantum IBM account, I suggest you to do these steps with me. I will share the link that you need to creating IBM account. I will share the link in my chat. Okay, you should go to quantum this link, the provided link here, and you will appear. You will land into page like this, and click sign in, and I am creating the IBM account. Follow me with me. Okay. And you should go to create an IBM account. Create an IBM account. Wait, wait a minute. Sign in and then create an IBM account. And here, I recommend you to sign it with Google because it is easy for you. This will take a while. Okay, I will give access to IBM. Okay, and click proceed. Follow with me. And provide the details they're asking here. Create account. I think you guys are follow these steps. Okay, my IBM account is created now. Okay, if you done these steps correctly, you will land into this page. IBM Quantum platform. Okay. This is the IBM Quantum platform looks like. Okay. We are creating IBM account for accessing IBM real IBM account, real IBM processors. Okay. In here, if I give a brief understanding about this platform, you can see there are quantum processors that are live on IBM. Here you can see several IBM quantum processors are appear here. These are the structure of details of an architecture structures. These are the quantum qubit architectural structures in each of these processors, and more details are appear here. Okay. Don't close the IBM platform, IBM quantum platform tab. Keep it as it is, and I will share you the notebook we are following today. Okay. I'm sending the notebook link to here. Okay. Before you starting this notebook, you should have to save a copy in Drive and then start the coding. Okay. Because this notebook is not editable because several people are accessing this notebook, so that I create the copy of Qiskit intro notebook. Okay, let's go through this notebook. Introduction to Qiskit. We know. First of all, I will. We all know the what is Qiskit, how it run, what are the steps we should follow for run a Qiskit program, and what is quantum circuit, and what are the how to and we create a IBM account for accessing real quantum computers. Okay, this is the outline of our introduction to quantum Qiskit introduction to Qiskit notebook. First of all, we are today we are learning about we are taking a Qiskit overview and installation, installing Qiskit, and we are set up. We already set up IBM cloud account, but we should have to take a API for our notebook and send our quantum circuit to real quantum hardwares. And we are learning about how to manipulate qubit, how to manipulate a qubit, and we learn about what is relative phase, and we learning about what is quantum gate, compilation of we learning about how to compile multiple qubit gates at once. And we are learning about measurement of quantum circuits, and we running quantum circuit in quantum simulators. We already talk about quantum simulators, and we send our quantum circuits to IBM quantum computer, and we deep dive into quantum computing by learning about multi-qubit gates. Multi-qubit gates by learning about quantum entanglement. Okay, this is a quick. I will, as we go through this notebook, I will give a quick recap of Qiskit overview again. Qiskit SDK is high performance, and it is have a very it provides a very useful quantum infrastructure facilities, and their core features are working with quantum circuits, operation and primitives, and get optimal performance from IBM quantum computers. And additionally, they provide transpilers, quantum functions, and runtime services to commit the quantum our quantum circuits for quantum hardwares, and it is flexible, faster, and have a good community contribution and improve accuracy. Okay, the first section is done, and then I move to installing quantum circuit and import library. In here, you can see I am installing three Qiskit libraries. In here, we installing Qiskit visualization part to ensure that we can upload circuit states and other qubit data, and this allow you to run quantum circuit on IBM quantum cloud back, and this is installation of IBM Quantum runtime, and this allows you to run quantum circuit on IBM quantum computers cloud backends, and it provides you to access to IBM quantum computer system and runtime environment. And this I am installing Qiskit AER. Qiskit AER is a high performance simulators we talk about previously. We talk about in our lecture slides, our session slides, and it lets you test and run the quantum circuit on your local computer with needing a real quantum without needing a real quantum devices, which means that we are doing verification phase in this Qiskit AER by using this Qiskit AER library. Okay, I run this cell, and I have installed all the libraries we need today, and I am importing Qiskit, and by using this command you can test what is the Qiskit version. As I mentioned, the latest Qiskit version is 2.2.2, and I am importing importing functions that we are need to run quantum circuits and do visualizations and measurements. I will go through one by one what are the why we are importing these functions. Qiskit Qiskit circuit, quantum circuit, it is used to create and work with quantum circuit. And state vector, it is represent and manipulate quantum circuits. And plot state is visualize the quantum state on QSphere. We learn we will learn what is QSphere later. And AER simulator, it simulates the quantum circuit locally. And Qiskit runtime service to access IBM Quantum cloud services. And sampler SP is used to sample measurement result from quantum devices. And this generate passkey to optimize the circuit. We talk about this generate passkey in our transpilation phase in our slides. And this is same as above, and this is optimal. This is an optional. This is array to latex. Array to latex. We importing this array to latex function to display state metrics in latex. And plot distribution is to visualize the measurement result and probabilities of our quantum circuits. And I'm importing NumPy for numerical calculations, and here square root. These are the functions and objects we are importing for our Qiskit compilation process. Okay, Qiskit circuit design process. Okay, the third section. I'm in third section, and I recommend you to follow with me, and it is more easy to you guys. Okay, now we are taking API from our IBM platform. This phase is need when we are run a quantum circuit in real quantum computer hardware. It means the 10th section of our notebook, but I am taking API and CNR codes for here because it is easy to go through the notebook. Okay, follow with me. In here, you should have in here I am importing Qiskit runtime, and you should have to take the API key. To take the API key, go here and create an API. Let's say Qiskit Fall Fest. Let's say Fall Fest. For Fest. Alright. And create the Fall Fest. And you can see the API key is created successfully. If you lost this API key like this, you should have to go view all, and all the API keys, IBM API keys are listed here. If you want to take in here, just say create and then copy. Copy the API key and paste it here. If you lost the API key, you can also take the API key from here. See, my API key is here. The newly created API key, QQ API key also here. See, you can take the API key from here. Okay, and we paste our API key, quantum API key in here, and then we should paste the CNR, customer reference number, and paste this here. Paste this here. Let's run this code. If you import your API keys and CNR account successfully, there should be no error appear here, and then run service. In here, you can see the state of your API call, and in this function, you can see what backends you can use. Which means the quantum processors you can access. Actual quantum processors you can access. As in here, you can see 4 quantum processors are available. Because of that, in here you can see this these two quantum processors, IBM Kingston and these quantum processors are not appear here because those quantum processors are not available. But in here, all this year in these computers are available for open instance. Okay. So we access the quantum real quantum computers, and now we are moved to again reminder, we need this step for doing this 10th step means running a quantum circuit in real quantum computer. Okay. Okay, let's move on to fourth section. This is the now we are starting learning about quantum computing. Okay. Manipulating quantum qubit. Quantum circuits. Let's talk about quantum circuits. In slides, I explain about quantum circuits. It is the fundamental unit of Qiskit. It is Qiskit. It is a quantum circuit, a sequence of instruction a quantum computer used to operate on qubits. And qubits have unique properties that allow you to computers to solve certain problems differently from classical computers. You can manually design quantum computers or use IBM tool to simplify the purpose. Simplify the execution. In this section, we will build a simple circuit and run it on quantum simulator for learning purpose. These are the links I provide you to learn more about quantum circuits. Before going into quantum circuit, we should have an understanding about a little bit about quantum mechanics concept. There are two main characters. There are many characters in qubits, but we focusing on two. Today we are focusing on two quantum characters. First one is superposition, and then quantum entanglement. Superposition is a qubit can be in state of 0 and 1 at the same time. It means it is a probabilistic approach. In classical computers, you just have only 0 or 1. Means classical computers are deterministic. The superposition allows the quantum computer to explore many possibilities simultaneously. And then quantum entanglement. Entanglement means a qubit can be linked so that the state of one instantly affects the state of another, even if they are far apart. This state, this lets the quantum computer solve problem in the way that classical computers can't efficiently done. Quantum computers are more very good at than classical computers, because quantum computers would factor huge number of in second. In fact, quantum computers can factorize huge numbers in seconds, like by using algorithm called Shaw algorithm. And also it can simulate molecules at the quantum level, which is nearly impossible for quantum computers. Now, this could resolve the drug discovery, material science, and cryptography. Okay. Before I move on to the quantum circuits, we should have an understanding about drag notation. Drag notation is introduced by a physicist called Paul Dirac. In here, there are two types of drag notation. One is Ket and Brown. The Ket represents a column vector in complex vector space, describing the state of the quantum system. For example, this is don't confuse these notation. These are just These are just mathematical notations. In this notation, we indicate this matrix, and in this notation, we indicate this matrix. In here, as I mentioned in here, as I mentioned here, ket 0 is a 0 state, and ket 1 is in 1 state, which means means the if the quantum bit is fully in 0 state, 0 ket state, that means the qubit is 100% to 0 state, and if ket 1 and ket 1, this means the qubit is 100% in the state of 1. Brown notation. Brown notation is Hamilton conjugate of the ket. It is a conjugate of ket. It is represent as row vector. This returns a column ket in a row for operations like inner products. In here, kets are always columns and bra are always row. You just for today's session, you just need to remember about ket notation. For more, if you are learning more about quantum computers, you also need to learn about what is bra notation and how to conjugate ket notations to bra notations. Okay, let's move on to basic operations of qubits and measurements. Writing down a single qubit state. Classical bit can only take 0 and 1. As I mentioned, it is deterministic. But quantum bits means qubits can be with can superposition with 0 state and one state simultaneously, or any linear combination of two. The most general, this is the general formula of mathematical formula of the quantum state. In here, we in the previous session done by we done in Qiskit Fall Fest, where Viduranga will teach you how what is this probabilities and how why we are scoring this probabilities for writing a qubit state. So I do not explain more about why we are take square root of probabilities. In here, by looking at this notation, we should have to get and understand the probability of measuring 1 is P, probability of measuring 1 is P, and the probability of measuring 0 is 1 minus P. This notation is indicating that. The parameter phi is represent the relative quantum phase between 0 and 1. We will learn about what is the meaning of the relative quantum phase later. The phase play a key role in quantum inference. Quantum inference is an quantum character. It's enabled to quantum algorithm to output the classical ones. Okay. Visualizing quantum states. Let's move on to how to visualize quantum state by using Qisphere. Qisphere, quantum state can be visualized using Qisphere, which map superposition and phase on sphere. These are the characters of Qisphere, but I am not explaining each of these points because you can't understand all of these points without taking how to change the state of the qubits by using gates. Okay, this is how we visualize visualize quantum state by using QSphere. You can make exactly same QSphere by using quantum circuit. The state vector in here, for this notation we call state vector. Remember that, okay? State vector. You can make exactly same QSphere by using quantum circuit. The state vector here we are using from 0 state. In Qiskit, the qubit is initialized in 0 state. Okay. In Qiskit, if we are initializing a qubit, the qubit is always in this state. This state called this is equal to this state. This is equal to this state. Means the probability of having 0 is 100%. So now we see the probability of measuring 1 is 1. Probability of measuring 0 is 0. Means the probability of getting 1 is 100%. Okay, let's visualize the circuit. The QSphere. In this QSphere, you can see this circle, and there is a small dot here, and this is the phase. This is for the indicating phase. I will tell you what is the phase and how to indicate the phase in this this QSphere. Okay, let's go to this section. In a QSphere, a visualization tool, I said that it is a visualization tool from state, and it is represent all the basis state of multiple qubit system as point as qubit sphere. Okay, these two later I will explain these four points. Okay. In the so this is not a superposition state. The qubit is 100% in 0 state. But if we need to make a superposition, which means the both the state, both the 0 and 1 state have 50-50 probability. We using this. We are indicating that superposition state by this state vector. So I am using Qiskit for visualize that phase. In here, you can see that 1 upon square root 2 for 1. This is indicating 1. This is indicating 1, and this is indicating 0. The probability of having 1 is half. Means the square root of this coefficient is come to here, and probability of having 0 is half, which means the square root of this coefficient is also half. And then we visualize our quantum bit. Now our quantum bit is in superposition state. Okay. Consider this state vector. In here, you can see that there is I. There is I imaginary number, complex coefficient in here. For taking the amplitude of state 0, we take probability. We take probability by squaring the coefficient in here, and we take the amplitude. The meaning of amplitude is probability. Don't confuse with it. Amplitude equals probability. The amplitude of amplitude is the coefficient. The probability is the square of the amplitude. Square of the amplitude. Square and modular square. Okay, we should take module in here and then square, and then we take imaginary probability by using by taking the modular and square of this coefficient, and then the probability become zero. Probability become half, and then you can see that probability of measuring 0 is half, and probability of measuring 1 is half. In this case of the superposition state, where the quantum phase is non-zero, non-zero. Okay. In the previous state, the quantum phase is non-zero. Okay, let's move on to what is quantum phase. In here, there is I told that there is imaginary number in here, but it is not effect for the probabilities, but it affect for the phase, relative phase of the qubit. I mentioned that the relative phase is in here. Okay, I can't find it. Okay, anyway, relative phase is the phase between state 0 and state 1. Consider this state vector. In this state, in previous states, there is no phase because there is no imaginary, or all the coefficients are plus real numbers in this state. But in here, we have imaginary number. For visualize this, we are using state vector for state vector, and in here, as we develop this quantum state in here, we are developing the this state by adding imaginary number in here. See, you can see a J to add an imaginary number and then visualize it. You can see the color is changed. Color is changed, but in here, the both colors are same. The meaning of this is if there is color difference between two phase, then there is a relative quantum phase, which means the phi is greater than 90 degrees. In here, the general equation of the quantum state, you can see phi. You can see phi. The phi is equal to 90 degrees when the for this state. To visualize that relative phase, Qiskit are providing this this color phase. See, you can see the phase for the state 1 is purple color, and there is no phase for 0 state. Okay. Okay, let's learn more about relative phase. I am not going to all the relative quantum phases here. I am just mention the idea of relative phase mathematically because the time because of the time constraint. We can't explain all the mathematical stuffs in relative phase, but I just run. I just visualize this phase. There is no. You can see there is no positive. There is no imaginary or negative numbers, which means all the coefficients have real positive numbers. So if we want to visualize this this quantum state vector, see here I write the square root 3 over 2 and 1 over 2. Then we are so we now we have visualized the quantum state in here. you can see these two dots are not similar. The size of the dot is indicate the magnitude of this coefficient, because zero state has high magnitude. Because of that, dot is large, but in for the this state, state one have half. You know that root 3 of 2 is larger than 1 over 2. Because of that, the size of those are not similar. Okay. And I also mentioned that there is no relative phase because the colors are same. And then if you then we are move to this phase. In this phase, you have imaginary number in your coefficient. This coefficient has no no positive real numbers. To visualize this, let's visualize this. I think I suggest you to do this with your. I will give to 1 minute. I will give you some time to do with your. I am copy the code in here, paste it in here, and I should have to change here, should give half, because the probability of having probability of measuring 0 is 1 over 4. The coefficient of 0 is 1 over 2, and the coefficient of probability of measuring 1 is square root 1 over 3, square root 1 over 3. But you should have to imaginary number. Imaginary number. Okay. There is a comparison. Wait. Okay. We complete. We design this. We make this state vector with, and in here there is a relative phase. Between 1 and 0. Because of that, colors are different. See, colors are different. You can see for the for 0, the phase is 3 over 2, and for 1, relative phase is 0. This is the mathematical explanation about how the how this become 3 over 2, and I will not explain how the mathematical how these phase come mathematically, but I give the notes you need to follow when you are go through with this notebook. Okay. And this is also quantum mistake. No, it is similar to this. I think I am duplicate that cell. Okay, we finished what is the meaning of the relative phase. Okay, let's move on to sixth section of our notebook, quantum gates. There are many quantum gates. There are many quantum gates. We discuss these gates in our slides. X0 gate. I will introduce the 2-3 gates in this. This is X0 gate. Actually, the meaning of X0 gate is bit flip. We are flipping 1 to 0 and 0 to 1. This is the matrix for X not gate means flip, bit flip. In here you can see the matrix and how the bit flip is happen in mathematically. And this is the Hadamard. We learned about the Hadamard. Hadamard is the need for the create superposition, and this is the mathematical metric transformation of how superposition is done for single qubit. And ZK is phase flip. Phase flip means we are not changing the probabilities, we are changing phase. What we are learning this section. And there is S gate. S gate applies for it's also a phase flip, phase shifting gate. Okay, this is how this is our Q sphere that are changing to various kinds of state because of the quantum gates applied for the quantum gates. See, if we are had a Hadamard gate for qubits, then it become a superposition. If we apply Hadamard gate for quantum bits that already in a superposition, and then it become and it's become to normal qubit. Okay, this is how we manipulate quantum qubit. Okay, these are the practical quantum circuits using a single qubit. This is how we indicate. This is how we indicate bit flip. We talk about this. These are the gates applied for quantum bit. This is Hadamard gate for superposition, and this is rotation by pi over 2, and this is rotation by phase rotation by minus pi over 2. Okay, let's do this task. Let's start by performing a bit flip. The goal is to reach in here. The task is to reach this state. Again, I will mention you that in default, bits are come from this in Qiskit. Qubits are in the state of 0. Get 0 by default in this state. Okay, we should have to change. We should have to change this state to this state. For this, what would be the gate should be applied here? You can see this is a bit flip, which means we are flipping the probability of the 100% probability of having 0 to 100% having probability of 1 by using X not gate. In here, if I explain the first of all, I'm about to explain the code in here. This is the function. This is a Python function. In QC, you are in this quantum circuit. We are initializing the qubit. In here, we are applying only one qubit for our circuit, and then apply not gate for the first qubit. We are indexing our qubits with 1, 2, 0, 1, 2, 3, not in 1, 2, 3. We are indexing 0, 1, 2, 3. As we are initialize one qubit, the index is we have only one index for this is only 0. If as example, if I put index as 1, there won't be an error. See, because there is no quantum bits for to do that, to perform XDA. So I am indexing first qubit as 1. See, if we apply XGate for the our qubit, the qubit become bit flip. The probability of having now the probability of having 1 is 100%. This is how we can create the circuit developing this biggest function. Next, we are creating a superposition. For superposition, we are using Hadamard gate. You know that Hadamard gate is used for superposition. We initializing one qubit and then apply Hadamard gate, and then the qubit become superposition qubit. See, the qubit becomes superposition, and also again small revise. This dot t is small, but this dot t is large because the magnitude of this is 1, and this for magnitude of this is 1 over root 2. Because we are applying Hadamard gate, and the bit become superposition qubit. And this is the circuit for Hadamard gate. And then we are combining about two gates for create this state. To apply this, we should have applied X gate first. We should have applied X gate first. QC X gate first, and then apply Hadamard. You can see that the qubit is turned into this state. See, the initially qubit was in this state. Initially the qubit was this state, and we are changing the state to this state by using NOT gate and Hadamard gate. NOT gate made X gate bit flip, and this is the circuit for above. And finally, we are creating. Finally, we move on to the complex numbers, and the goal is to reach this state. For to this state, in here I mentioned several gates. See, these are gates that can be can do quantum transitions. These four gates are for probability transitions, but for these two are for phase transitions, quantum phase rotations. For this, first we are apply Hadamard gate for first we are apply Hadamard gate for make superposition, and then we apply SG STG gate for create this state. Now you can see we are create this quantum state by using Hadamard, make the Hadamard Hadamard for superposition, and SDJ for create a relative space, relative phase. Okay, these are the gates that are several gates that are provided from Qiskit, and you can use these gates for more complex tasks done by using Qiskit. Okay, the section number 6 is completed, and then we are moved to compilation of multiple qubit gates at once. In Qiskit, we are not applying gates only for a single qubit. We can use multiple. We can compile multiple qubit at once. See, this is a quantum circuit with multiple circuit Q0, Q1, 2, 3, 2 and 3. I suggest you to apply Hadamard gate for this circuit. We visualize the circuit as circ, and then we apply and we apply Hadamard gate for this. And the circuit, the Q0 circuit become changed. I am applying Hadamard gate for Q0. Okay. See, we apply Hadamard gate for Q0. If I apply Hadamard gate for 1, then circuit become changed. Circuit change. Likewise, we can change and create a circuit by using Qiskit. This is the compilation of multiple qubit gates at once. Okay, then move to measurement of quantum circuits. In previous sections, we are only creating quantum circuit, but we should have to measure them. In quantum, we cannot take probabilities by looking at one qubit. We should have iteratively run our circuit for several times, and then measure our the state of quantum circuit. In Qiskit, the only measurement you can do directly in computational basic measurement. Each qubit you measure gives one bit result, 1 or 0, and this result is stored in classical register and specific rotation. Resultant is stored in the register at a specific location. We apply we create a Hadamard circuit with Hadamard gate in here, and then but we do not apply measuring bit for this. To apply measuring gate measuring bit, we should have to give this argument. Which means in this first argument, Qiskit mentioned about how many qubits are importing, and in second argument, it mentioned about how many classical register are importing. If I run this circuit, see new classical bit is import to our circuit. And we need to add measure gate. We are measuring 0 bit and store it in index number 0 classical bit and draw. Okay. See, now we are create circuit with measuring gate. Now we can get the output of the output come from the qubit 0 and store it in here. Okay. This is how the measurement in the quantum circuits are done. And okay, now we are moved to run a quantum circuit in simulator. In our slides we talk about the quantum simulators. We talk about AER simulator, and I am using AER simulator for run our circuits in our Qiskit program. I create the previous created quantum circuit, and then I should have to transpile this. You remember that we have 4 workflow steps. First one is creating build the circuit, and then transpile it. We do the transpile here. Transpile circuit on simulator. Simulator means this simulator. AER simulator. And we are committing our job to our simulator by 1024 shorts means qubits. We are iteratively run this circuit for this amount of attacks, and then take the count as we are applied Hadamard gate. Among these shots, 488 are for 0 state, and 156 are for state 1. The reason for applying large number of shots is, if we apply only 2 shots, the probability is not we can't get the probabilities as we expect. See, if we run this for several times, the probability might become if we sometimes take 100% probability for 0 and 100, it might output the 100% probability of 0 or 1. And because of that, as we are dealing with probabilities, we should have to have large number of short iteratively. We should run our circuit large number of iterations. Okay. So this is a simple task. Simple task to you to do using Qiskit. I recommend you to do after this session. After this session, this is more about quantum gates. We can use complex quantum gates, these type of quantum gates, and take the probabilities. Do this task after this session. This is an exercise. This is the mathematical explanation about this circuit. Follow this up, and let's move to the same. I duplicate this. Sorry. Let's move to run our circuit in real quantum computer. Okay. So we create circuit in here. we create a circuit in here, the circuit name called circ. To run in real quantum computer, I will take this circuit. Sorry. Will take this circuit. This circuit. I am committing this circuit for. I'm committing this circuit for our real quantum computer. The circuit name is a circ. Okay, this is the library imports we done in previously. In here, I am checking the least busy quantum computers. In here, you can see that quantum computers are live. There are several people are committing their quantum computers for these servers. Because of that, we should check what is the least busy backends, and then we are using this backend for to commit our quantum circuit for this backend. Okay, and this is the the pass manager step with sampler, and then we run the circuit in pass manager, and we have do the transpile because this is the second step of our workflow. We transpile our circuit, and the circuit is killed. Okay. If you do the steps successfully, you can see processes you are committed for real quantum computers. The ID number is this ID number, and this is similar to this ID number. And job is queue. Might take some time to start the progressing of our quantum circuit. Because of that, I will not run this circuit if I run these cells. If I run these cells, I can't go for following cells. This is how we are running quantum. How to commit quantum circuit to real quantum computers. As the time is over, we should stop our session today. We complete 10 sections in our notebook, but because of the time constraints, I am unable to complete the multi-qubit case, which there is the details about quantum entanglement. These are the reference links you can follow to learn more about quantum computers. We do 10 sections in our notebook. I suggest you to study multi-qubit gates too, but by using Qiskit resources. And today's session is finished, and I am open to questions. I will provide these slides for you for learn more about Qiskit SDK. These are the installation process. We already done them. If you have any question, please ask. I think most of you guys have There's no questions. If you have a question, you can put your questions to our WhatsApp group. Okay. And thank you all. Have a nice day. Dhananjay, are you there?
Hi. Thank you. Thank you so much, Lisitha, for that amazing session. We learned a lot today, and thank you so much again. Now, shall we take a group photo to remember this moment? So I'll provide the link to the background picture so that you can download it. I've provided the link in the chat section of the meeting, and then we'll take the group photo pretty soon. So set up your background picture, then we'll take the group picture. Thank you. We have provided the background, like the virtual background on the WhatsApp group as well. If this is all, shall we take the group photo then? All right. Okay. Then say cheese, and then we'll take the group photo. 1, 2, and we'll take another photo. Pick 1, 2, 3. All right. Okay. Thank you so much, and we'll see you on the in-person workshop. And thank you again, and have a good night.